second trial might take a little bit more beyond the time dedicated. So we'll do one trial. All right, are we together? So let me share with you the PowerPoint. So we'll go over the steps that are to be done. So the whole idea basically is to be able to measure the specific heat of an unknown metal. So we have an unknown metal, okay, some metal with an unknown identity. So trying to figure out the specific heat of that unknown metal. Now, specific heat by definition is the temperature, the amount of heat required to raise the temperature of 1 gram material by 1 degree Celsius. So if you carve out, let's say 1 gram, let's say, assume here's your unknown metal, and then let's say here's the metal. Okay, so here's the metal unknown. I don't know if you can see them. So assuming here's the metal unknown. So I'm gonna scoop out 1 gram of that unknown metal. And then I want to keep delivering heat to it, keep raising its temperature up until that temperature becomes 1 degree, whatever that room temperature. Keep adding heat up until that metal, that 1 gram of that metal unknown raised up by 1 degree. How much heat it took up to raise its temperature from the initial temperature to final temperature by 1 degree is called specific heat. So it's a little bit more unique definition. Okay, the question is, how do you approach the measurements? So the measurements to be approached using what's known as the calorimeter setup. So using this typical setup for all these thermochemical reactions, including figuring out the specific heat of an unknown metal. So I want to use that setup that has the following. So it has a thick-walled insulator. So this is styrofoam insulator. Other materials are possible, but then this is a good insulator. Just made out of styrofoam. The cover basically just not matching styrofoam, but then just a cover, plastic cover that has a mountain thermometer. So I'm using a thermometer and a place slung in that thermometer, and then the walls of that insulator. This time around, styrofoam. The setup is primitive as far as the setup. However, the setup is good enough to give us a good amount of information to identify the unknown. Okay, so I'll give you some aspects of the unknowns and some possible unknowns. So you guys, at the end of the experiment, you figure out the specific heat of that unknown and try to identify the unknown. So let's see how this is to be done. All right, so the setup is as following. So I'm going to measure a specific amount of that metal. It doesn't matter how much. Should I measure 1 gram, 10 gram, kilogram? It doesn't matter the initial amount. Specific heat is intrinsic property. It concerns with the building of that material. Intrinsic to means careless about the amount or the volume of that material. It just concerns with the building, the interconnections, the atomic, the molecular picture of how those building blocks of that material is made out of. So the property shows either one, if you measure 1 gram, 10 grams, a kilogram, it doesn't matter the amount that you scooped and measured, okay? It's gonna reveal itself regardless of the initial amount. So it doesn't matter the initial amount. I'm gonna just challenge maybe 50 grams or so of that metal. I'm gonna heat up that metal initially to a specific temperature. So I'm choosing to heat up the metal inside hot water, hot boiling water. So that means the initial temperature of that metal has to achieve the same as the hot water, but I need to measure it. I need to verify it. It's not typically 100. The typical boiling temperature of that water is 100. If you snug in that metal inside that boiling water, don't assume to be 100, it has to be measured. So we're going to measure that initial temperature of that hot metal. And then on the side, we'll want to prepare the calorimeter. So this is the calorimeter that is made out of a styrofoam. And then we want to prepare a thermometer to collect data. So once you're ready, as far as to transfer that metal, so you uncover the lid, scoop that metal from that tube, and then eventually deliver it straight into that calorimeter. And then wait until that process finalizes itself, and I'll explain to you shortly what does it mean. So the process will finalize itself into some number, some temperature. So let me ask you this. Let's say if you're trying to do something, trying to do some measurements, let's say if you want to measure temperature of a material, let's say baking choose something. Okay, so here's a beaker. Okay, so what's the initial temperature of that beaker if I want to measure the temperature change? So I guess you touch it with thermometer and try to measure the initial temperature. Okay, so we're definitely clear about that concept. Let's say I want to heat up that beaker. And what must have been the final temperature upon heating an object? What do you think? I don't know. Well, it depends on how much heat you delivered. So the final temperature is whenever you decide to stop making the measurements, correct? So here's my thermometer. Okay. So here's my beaker. Look, so this is an object. Stick around with me. Okay, so here's the object, an object. It's not a thermochemical process. This is an object. So the initial temperature, here's my thermometer. Just check the initial temperature. That's that. Now I want to heat that object. So continue adding heat until that object is gotten hot. And then here's the thermometer once again. And then you stop the measurements, correct? So you only took two measurements, the initial and final. So the final temperature, whenever you decide to measure that beaker at any point of heating, correct? Let's say if you want to heat it a little bit less, so whatever that temperature of that final heating, that would give you the final temperature. The final temperature is based on what you thought the final measurements of taking the temperature. True? This time around, the final temperature of thermochemical process is not the same. Which is a little bit confusing. So let me explain to you why. The final temperature of the process has to be measured at the beginning of the process, before you start the process even. For example, let's say, my analogy, let's say you walked into a room with a hot drink. So when you walked into that room, I say, stop right there at the door, measure the initial temperature. I gave you a thermometer, so you'll be able to measure the initial temperature of that hot drink. While there, you saw at the door, I'm asking you to measure the final temperature as if you walked in and you stayed in the room for half an hour. But you're still at the door. So at the time of measuring the initial temperature of that hot drink, I'm asking you, can you measure the final temperature of the hot drink? But you'd say it doesn't make sense. I mean, you can measure the initial temperature. So here's my hot drink one more time. So hot drink as you walked in. This is just an analogy. What's the initial temperature? Well, just plug in the thermometer, measure it. What's the final temperature? Well, final temperature is, well, what does it want to do with that hot drink? Once I let you in the room, definitely the hot drinks will cool down, get cooler. So eventually the final temperature is whatever that you decide to measure that final temperature. That's what you thought, which is wrong. So for any thermochemical process, the final temperature has to be measured at the same time of measuring the initial temperature. At the same time, the initial and final temperature needs to be measured at the same time. Both needs to be measured at the same time. And it doesn't make sense. Yeah, very difficult. How do you measure the? So as you walked into that room, before you're walking in, I'm asking you to measure the initial and final temperature of that hot drink. It's incredible, okay? So it's not doable. So the reason why we're gonna do that final measurement, the final temperature, by what's known as extrapolation, okay? I'll show you in a second how to do it using software. So tonight we're gonna be using software to measure the final temperature by the process of extrapolation. So to begin, let's go back. So we all turn to page 99 or 100. So we're going to measure first a small amount of water. So we're going to add a small amount of water inside that cup and measure specific amounts of that metal. Then heat up that metal, then transfer it into that water, into that cup, into that styrofoam cup, and then figure out the initial final temperature at the beginning of the process. At the beginning of the process. All right, so hopefully you'll digest what was it about to be done. So now, so this is what I'm trying to say. Okay, so eventually you're going to see on the board a graph between time on the x-axis and on the y-axis temperatures. So at the beginning of the plot, so whatever that straight line showing with time passes, the same temperature, it means this is typically the room temperature before any process kicks in. Once you add a metal, the water inside the calorimeter is going to heat up a little bit. So temperatures will rise up, continue on rising until some point, eventually it's going to slow down. It's going to jump, it's going to rise. Eventually it's going to plateau a little bit, then it's going to slow down back to the room temperature. Okay. So we're going to see the following plot that has three portions. The first portion represents the room temperature. The jump indicates the amount of heat delivered to the water by the heated metal. That plateauing, it means the temperature cannot rise anymore. It'll plateau for a second, maybe for a while, and then eventually it's going to start dropping because that wall of that container is not 100% insulated. Okay, eventually whatever that hot material is going to cool down eventually. Okay, so it's going to somehow go down and decrease in temperature after a while, back to room temperature. Okay, that's always the tendency of these containers with the stuff inside. And that feature is going to be shown later on. So I'm going to track that feature of reducing or decreasing temperature. I want to extrapolate using the plot back to the initial time mixing, which is at the initial time mixing, assuming here's the kink between the initial temperature and some activities occurred. At the initial time of mixing, the intercept of that vertical line with the line drawn from that straight line of the later on section of that curve is going to give me the final temperature. So that intercept point is my final temperature. So let me explain to you how to do it. All right, so back to the measurement. So first, I want to measure any amount of metal. Okay, so I guess any amount, let's decide on 50 grams. So just follow me with the measurements. Can you see that screen? Okay, so I'm going to zero that screen. So I'm measuring roughly 50 grams of metal. I guess one more bees. Okay, that's good enough. All right, so that's good enough. So record that number. So what we have, can you see those numbers? What's the mass of the metal?
Appears to be 49.41 grams.
Right, so record that number. The next step, I want to measure the mass of water. So I want to snug in a small amount of water in here. So I guess let me measure 50. Okay, comparable. What you want basically is to have enough of water initially inside that calorimeter in such a way as to cover the size of that metal. So if this is the beaker, so notice, so what's the size predicted based on that amount of metal? 20, 25 milliliter. Agree? Can see it? Because this is about 50 milliliter beaker. So this is a 50 milliliter beaker. And this is the amount of that metal inside that beaker. So I guess somewhere around maybe 20 is 20. So still, I need to make sure that whatever that water inside that cup should be at least above and beyond that volume. So I want to measure, let's say 50 milliliter. So 50 milliliter of DI water, somewhere around 50 grams, agree? So let's tear that calorimeter and deliver 50 grams, meaning add in 50 milliliter. I can add a little bit more. Okay, so since I measured 50 grams, almost 50 grams of metal, let me make this one around 75 milliliter, just to make sure. Okay, good enough. All right, so that's the initial mass of water. So record that number. So the initial mass of water, can you see that value? Can you read that value for me?
74.54.
Very good. So that's the mass of water in the calorimeter in grams. The next step is I want to heat up the metal. So let me show the setup. So on the side, I was heating water. So I have a container, a beaker, sizable beaker, 600 milliliter. I added some water. So now it's already boiling. So I want to insert the metal inside that large test tube. And then I want to leave it or submerge it inside that hot water for at least 10 minutes because it would not heat up right away. It's going to take a while. So I'm going to keep heating until at least achieve a good number, very close to that heating water, which is boiling water, which is 100 degrees. It may not be 100 degrees, but I need to measure it. Okay, so first, carefully transfer that metal that we measured into that dry test tube. Okay, so here's the transferred process. Snug it in and keep it suspended. So notice the hot water completely. So notice the hot water completely covers. So above, let me just so the hot water, can you see it? So here's the level of that metal. And the hot water should be above that level of that metal, just to make sure all the metal is heating up, just to make sure everything is working and hot metal receives a specific temperature without prediction. I don't want to predict the hot metal is the same as the boiling temperature, 100, but I want to measure it. So here's my thermometer. So I want to add in that thermometer on top of that test tube. So I'm snugging that thermometer on top of that test tube to be able to measure what sort of environment inside that test tube. Okay, so a way to read the temperatures. So I have the thermometer. So the thermometer is plugged into the screen. So here's the thermometer screen. So right now it says 31. See it? So that's the thermometer, the temperature inside the metal. So inside the metal, the temperature so far is still cold. Now it's rising up. So let me just put that in the background to be able to see both. You see that? Can you see that temperature? So now that temperature, which is the temperature of that metal inside that test tube. All right, so on the side, I prepared the following calorimeter. So this calorimeter has in it so far the measured 74.54 grams of the eye water. And I plugged in the thermometer. So here's another thermometer. And I'm ready to, or I'm waiting for that metal to heat up. I'm going to keep monitoring that temperature until that temperature of the metal would say somewhere around close to 100. Will take a while. I guess the hotter the better. Okay, so any temperature above 50 will do. It doesn't matter. It doesn't have to be exactly 100 or close to 100, but the hotter the better as far as the results. All right, so far the temperature is still under 40. So it's going to take a while. The temperature. So temperature. So temperature of that hot metal is achieved or transferred from the air above it. So what surrounds that tube is water, boiling water. What's inside that tube? Just air, the metal and the air. Eventually, so by convection is what gets the air above that metal to be heated. And and conduction basically, because the water is hot and boiling and touches the surface of that test tube, eventually by conduction, it's going to conduct the temperatures. But since these metals are like tiny spheres or tiny assemblage of the metal beads, they're not connected. So conduction would not work. So portion of it basically based on the contact. If there's a contact, so heat will go from place to place by conduction based on the contact. If there's hardly contact, it waits for the air in between them, because he's one molecule, he's another one, or he's a cluster of metal, he's another cluster, maybe touching by one point. You need a complete contact, so transfer heat from one to another by conduction. If there's separation and air in between, how he's going to go from place to place? Convection. He's going to hop into the air onto the other portion of that metal. So it's going to take a while. So there's a combination of conduction and convection. Eventually, it's going to allow the temperature of the metal to rise up. I'll give it a chance for 10 minutes. So let's time ourselves. So right now, 7:25. So let's give it a chance for 10 minutes. Let's see whatever that temperature is going to be at. We're going to transfer it, whatever, after 10 minutes. Okay. Because there's no way for that temperature to achieve the same as the boiling temperature. And I'm presumed to have 100 100 boiling temperature for that boiling temperature, for that boiling water. All right. Now for the calorimeter setup. So here's the preparation part of it. So I'm preparing a software. So that software has the following features. So I'm going to go to that clock and just let it go continuous, either by set time. So you can collect data based on set time, or by continuously collecting data. So I'm going to set it to continuously collect data. And then I'm going to just wait until I'm ready for that temperature of that metal to achieve the highest. Okay, and so far the temperatures. So temperature is at around 53 and increasing. That's a good part. All right, so we're gonna wait until 7:35. All right, so back to that page 99 or page 100, depending. All right, so let's write down a few facts. So the temperature of the hot metal, we're gonna leave it alone until we're satisfied with the hottest temperature on that screen of the metal. So we're gonna just leave it alone. But we can write down the initial temperature of the water inside the calorimeter. All right, so line number 3, third line, that would say the third line, that would say the hot temperature of the metal. The initial temperature of the metal is the hot temperature of the metal because I'm trying to heat it. So the third line is, leave it blank for a second. I can answer the fourth line, the temperature, the initial temperature of the water inside the calorimeter. Okay. And what's that temperature? Can you tell me what's the initial temperature of the water inside the calorimeter? Because I measured almost 75 grams of water inside the calorimeter. And what's that temperature? What's that initial temperature?
Is it
That water inside the calorimeter?
Celsius?
21.3, right? Let's write down that number. All right. So how is the temperature going on this side? So it's still in the 50s. So I have another thermometer. So this one is a little bit limited because it has that little bit fatty end, and it does not allow to go nicely inside the test tube. I can use another thermometer. So this is a little bit more, like a little bit more robust way. So what I've done basically, I just removed the first thermometer because that initial thermometer that is supposed to measure the temperature of the metal has like a little bit more wider, like short tip and wider body at the end where the electronic is. So I removed it and I substitute that temperature with another thermometer. So that thermometer has that look. It's a little bit more slick, a little bit more thin. I'm able to go as deep as the metal themselves. So I'll be able to measure at the metal itself. Okay, so I'll be able to measure the temperatures right at the metal. All right, not bad. Now the temperatures are reading 79 and climbing. You see those temperatures? Okay, not bad. So it is increasing and increasing rapidly. But let's see what's the hottest. So I still have another 3 minutes. But 84 is pretty good.
Where is the temperature?
So this is measuring. So this screen right here. So this screen right here is measuring that 85.3 so far is measuring the temperature of the metal. So I'm measuring the temperature of the metal, and he's the thermometer. So he's the thermometer measuring that temperature. Okay, and here's the value. So this is measures the temperature of the metal inside the hot water. The second thermometer, got two thermometers. The second thermometer, which is this one, is knocked into the inside the calorimeter and measures the temperature of the water, because I measured almost 75 grams of water inside that calorimeter. So the second thermometer is measuring temperature of that water inside the calorimeter. Okay. All right, so far so good. So temperature so far is almost 89. So let's give it a chance until I see a number that does not change, and within a minute, then I'll accept it. So far it is changing. So this is almost my 9 minutes, entering the 10th minute. But temperatures keeps on rising. So I want to see that temperature not move in or mean to be with the same value for at least a minute. Then I'll scoop it out and dump it inside that water, inside the calorimeter. I guess there's a cooling, right? So I got 90, but then I guess cool down a little bit. Even the temperature inside the calorimeter warmed up a bit. Temperature went up from 21.3 to 21.6. So he's 90. So let's monitor that at 90. If there's no waiting chance to deliver hotter temperature at 90, I'm going to just stick around to 90. So I spotted that at 90.2. Let's see how stable it's going to be. Yeah, so it's not moving. So now it's flickering to 90.3, between 9.2 and 9.3. But within a minute, if that value does not go up drastically or go down drastically, we're going to just accept it. It looks like it's not moving. Agree? So right now it is at 90.3, but it's not moving. So I guess if we sort of like a stuck at around 90.3, it's going to take a while to jump to 90.4, I'm presuming. So I guess we can stop the heating of that metal. And then I'm going to transfer the metal straight into that calorimeter and follow the software. But before, let me initiate the software. So once again, checking on that timer, continuous, pretty good. And I'm going to start the software. So easy collect. So now the software is starting. Yeah, remains to be solid at 90.3. So let's record the initial temperature of the metal as 90.3. So the third line, temperature of the hot metal. So that is the initial temperature of the metal. It is at 90.3. Agree? It's not changing. All right, so we're just about ready to transfer the metal. So just about ready to transfer the metal. So I want to position the two together.
So the 90.3, that's the temperature of the hot metal.
That was the temperature of the hot metal. That's the initial temperature of the hot metal.
Okay.
And then I'm ready to transfer it straight into the cold water inside the calorimeter. Okay. So I want to bring the two to be so close as possible. So I'm going to remove that thermometer. So it's no longer measuring. And now I want to, so the technique is by taking the least amount of time. So that transfer has to be done with the least amount of time. So I'm going to keep it and keep that metal inside the water. I removed all the obstacles while the software is running. So I'm going to just shove that cover. I'm going to remove that cover for a second, add the metal quickly, recover. So you're going to end up having some sort of a zigzag on that screen. So that's the result of just shoveling the two and add in the hot metal. Okay, so it's still measuring the temperature in the water. So I open the calorimeter. Okay, the thermometer still measuring the temperature of the water. So use the metal. I guess so give them enough of shaking. So all the metal now surrounded with water. So we just keep it for a while. And shut off that water. So now I'm done with that water. So as far as the calorimeter, so I'm trying to tape it in such a way as the cover remains to be a snug fit and remains to be tight. So that's the calorimeter. All right. Let's see what we've done. All right. So now I'll be waiting for the results. It's gonna take a while. So what's it I'm waiting for? So in that now software, So I'm looking at a graph of time versus temperature. Time is on the x-axis, temperature is on y-axis. So let me just, let me reassign that value. So I've just done some enhancement, just cosmetic. All right, and then I'm going to squeeze and see exactly what's going on this end. All right, so at the beginning, so this is what happened. So at the beginning, so as I removed the cover of that calorimeter, eventually I allowed that hot metal. I guess some beads come somehow just cluster one little area and the thermometer sends extremely hot temperature, but eventually the rest of them, as you cover them with water, eventually they're gonna give us like a more robust, more sort of an overall temperature of all of them to be collected, not just the ones that are suddenly touching the, because when I transfer it, the whole area is very tiny, and you transfer some beads, and eventually some metal is going to touch that thermometer sensor, the metallic portion of it is going to somehow spike. But then, so don't worry about that initial spike, just an artificial based on that beads are touching the sensor straight, but the rest of them are the overall behavior of all of them inside the water. Okay, so I'm going to rely on the rest of them behavior, that line. What I'm waiting for until I satisfy with the collection of data. So I'm waiting for that line to slightly go with a slight negative sloping. Okay, so mounted those temperatures right now at around 26.2. So I'm waiting for that temperature to dip a little bit, to go down to 26, maybe 0.1 or 26. Let's see how it's gonna occur. So I'm waiting for that temperature to dip a little bit. Right now, it is at around 26.2. So it's gonna take a while. So I'm gonna give it a chance of 10 minutes or so, 10, 15 minutes to cool down a little bit. All right, so right now it's not giving me any sense that it's gonna go down, but let's see if it's gonna go down a little bit. All right, so I'm waiting for that 26.2 to say 26 point, so say 26.1, then 26.0, something like this. All I want basically is to have that feature, which is sloping in negative direction by slight sloping. So slight sloping, that would give me enough of handle to analyze data correctly. Because I want that line. Okay, let me just show you exactly what I'm waiting for. So what must have occurred? That's what I'm waiting for. So I'm waiting for, so here's the feature of that plot. It's gonna jump after dumping the metal. Eventually it's gonna somehow slope in a negative direction, because eventually he's gonna get lost. So he's the calorimeter. Eventually leak, and he's gonna deliver, is gonna turn that temperature from hot to cold slowly. So now it's flickering between 26.2 to 26.1. It's gonna continue on going down. Eventually it's gonna go down, decrease until the room temperature, whatever that room temperature. Agree? Because that container is not perfect insulated. Okay, so that feature is going to help analyze the final temperature. The final temperature, we already missed it. So here's the misperception. So for any process except thermochemical process, the initial temperature is initial temperature. These are in common, but then the final temperature, especially for the thermochemical process, only true if that to be measured at the beginning of the process. Where's the beginning of the process? Right there. So whatever that action that took place, that's the beginning of the process. At that beginning of the process, the initial temperature is whatever that initial temperature, somewhere around, what is that, 21.8 something, okay? But the final temperature is not whatever that final temperature shown on the graph, on the plot. It's not. Final temperature should be measured at the beginning of the process, should be measured there, at the beginning of the process, which is impossible. So we always measure the final temperature at the same time we measure the initial temperature. So this is our technique, especially for the thermochemical process. So thermochemistry requires just primitive tools, thermometer and calorimeter, and sometimes timer or electronics, as I'm showing. But with these primitive tools, be able to measure lots of things: specific heat of metals, specific heat of solutions, heat of vaporization, for example, enthalpy of dissolving salt in water, enthalpy of reactions. So be able to measure a tremendous amount of measurements and informations. And they're all scientific, they're all true, as simple as utilizing and using thermometer and calorimeter, which is styrofoam, cheap material, plus maybe a timer or maybe a software. So that combination will give you access to be able to measure many materials, many aspects of scientific constants. So I'll wait a little bit more until that value becomes 26.0. Then I'll go ahead and measure the specific heat. All right, so that feature is very important for me as far as the slight negative sloping. Once I come up with that a sense of negative sloping, I'm going to create a straight line. So I'm going to select a portion of it and create a straight line based on that negative sloping. I'm going to go back to the initial time mixing. I'm going to create a vertical line. So here's the initial time mixing, assuming. So here's the final temperature, which is we already missed. The final temperature is higher than the hottest temperature shown on the plot. Definitely, this is an exception. So that little spike in here is just artificial. I guess few beats comes in and contacted. So if this is the thermometer and that's the sensor portion of that thermometer, a few beats of at around 90 degrees straight contact that sensors, the sensor is going to jack up its temperature, still surrounded inside the water, but then that temperature that would give us hotter values, which is not acceptable. So these are artificial jump. It's not part of that curve. So most likely the curve is going to bend at around this area. But no matter what's the temperature shown on that plot, the final temperature is always higher. If this is an exothermic reaction, meaning the temperature after you mix it to is hotter, we call that feature exothermic reaction because temperature increased. The final temperature is always higher than the highest temperature shown on the plot. So the final temperature is not there, it's not there, it's not there. It's not when you decide to stop measuring. Any other processes, let's say if you're traveling and someone said, okay, so what's your initial speed from the idle car not moving? You would say, okay, 0, but then, okay, go ahead and just move your car and tell me the speedometer. Okay, so whatever that measurement, it's called the final measurement, whatever that you decide to measure it. So it is at 12. The final temperature for the thermochemical process is not when you decide to stop the measurement. So that's why I kept saying it is already decided for you. And it's already occurred at the beginning of the process and you already missed it. Should be measured at the beginning of the process, which is impossible. How do you measure it? And the process did not kick in. You haven't started yet the process, but you need to measure the final temperature of that process that haven't started yet. It's kind of awkward, yeah? that will make it impossible to measure. The reason why, we have to measure it using software or plumbing. All right, so where are we going with this? So I'm waiting until that temperature goes down to 26.0. It's going to take a while. So not so bad for that cheap container. So this is just a few bucks, and gotten that container with the least amount of expenses. But look at the robust temperature inside of it. Yeah, it just went down from 26.2 to 26.1, and it took a while to get to that temperature, I guess. But I'd rather see it going down a little bit further. All right, so let's put a few things together. All right, so by the time the temperature goes down a little bit more, so let me just move the setup. Okay, so on the side, let's analyze what we have. Okay, so the theory goes this way. The amount of heat. So I'm going to represent the heat with that letter Q. So that's the heat exchanged by the metal. So here's my thermometer. Let me just bring another setup. So assuming here's another setup. Here's the cup. Inside of it is water. And I dipped in metal, heated metal. Now, the water and the metal together exchanged heat. All together, upon the exchange at the end of the day, so let's say if the metal delivered heat, because it's going to cool down, it's going to deliver heat to who? To the water inside that calorimeter. Water took up that heat coming from that metal, and it's going to heat up a little bit. It's going to increase the temperature. The metal, however, its temperature decreased from the initial hot temperature to a lower temperature. Both are going to wind up having the same final temperature. But the initial temperature of the water, the cold water, is cold. The final temperature is the final temperature of that process. The initial temperature of the metal added is hot. It's going to wind up having the same final temperature of together the water and the metal. So the same as, let's say, me and you in one room, let's say, by analogy, and I took out $5 out of my bucket and I give it to you. So I've lent you $5. Okay. So as far as your point of view, you gain 5. My point of view, I lost 5. At the end of the day, together, while being inside the room, $5 out of my bucket into your bucket. At the end of the day, well, what's the amount of total change of the amount of money inside the room? Nothing. There's 5 out of my bucket into your bucket. But eventually, if I have 5 and you got none, eventually the 5 get out of my bucket, land it into your bucket. At the end of the day, there's no difference in the total amount of money in the room. That's what I'm trying to say. So I'm going to equate it to, or if I add the amount of heat exchange, the heat came out from the metal, Q sub M, plus the heat exchange by the water. So I'm going to symbolize that as QW. All that heat exchange, based on my analogy, will add up to 0. Agree? All right. So now let's solve for that Q sub M for the metal. So Q sub metal, the amount of heat for the metal equals. So moving over QW for the water to the other side. So that belongs to the water. QW. So it takes on a negative value minus Q for the water. Okay, so substitute based on what we know. Okay, every Q term, every heat term has 3 simple terms: mass, specific heat, and delta T. So memorize this on the side. So every Q, every Q, which is heat, this is heat. Every Q, every term that represents heat has in it 3 terms: mass, specific heat, and delta T. It has always 3 terms. So that means Q for the metal should have in it the mass of the metal, specific heat of the metal, delta T for the metal. Okay, so let's write them down. So I'm gonna write down all the terms, or the three terms that belong to the metal, which is the mass of the metal. What's the mass of the metal? What was it? I measured 49.41.
49.41.
Right? So 49.41 grams. Multiply this by the specific heat of the metal. Well, it is unknown this time, so I'm going to leave it as unknown. So this is the specific heat of the metal. So this the metal. Multiply this by the delta T for the metal. What was the initial temperature of the metal? Because I want to figure out delta T for the metal. Delta T is always T final minus T initial. What was the T initial? What was
58.2.
So what was it? 21.3 or 2, you said, right?
That's the heat of water.
The initial temperature, I'm sorry. So the initial temperature of the metal, it's a hot metal. So therefore, what was the temperature? 90.3. So the initial temperature of the water, because the water was heated inside the boiling water. And remember that number, 90.3 Celsius. So that was the initial temperature for the metal. The final temperature is coming up. So that I don't know. Okay, so we're gonna wait. So I'm gonna write down the following. So the term that goes under for the delta T measurements for the metal, T final, which is we don't know. I'm gonna measure it later on, which is coming up. And that number does not go down. Okay, very good. All right, so I guess stuck at that value, which is fine. So T final minus the T initial. What's the initial temperature of that hot metal inside the boiling water? It was 90.3. So I'm gonna write down 90.3. Equals on the other side, here's the negative. Now, every Q term, every heat measurement has the set of three terms, mass, specific heat, delta T. Now we're going to concern all these measurements with the water measurements. What's the mass of the water? So the first term for the water.
40 or 74.5.
Right, so I'm going to write down 74.54 grams times the specific heat for the water. What do you think? What's that number? What's the specific heat value for the water?
4.184 joules.
Very good. So 4.184, and this is in joules per gram Celsius. So this is in joules per gram Celsius times delta T for the water. All right, which is typically the final temperature, which is coming up, minus the initial temperature. And what was the initial temperature for the water? I guess that is the measurement. Let's just get an idea of what's going on. So this is, yeah, so that temperature does not go down. So we can stop the process, okay, if you want. Okay, so I'm gonna go back and just stop that process, which is fine. Okay, so the process did not go beyond that number. Okay, so it resists to go down. All right, so here's the cursor. Okay, at the initial temperature, and can you see those values? So can you look up that window, the X and Y, and locate the initial value of that temperature? So that initial temperature, can you see that Y value of the cursor? Can you look at
21.85?
Right. So 21.85. So I'm going to write down so this is 21.85. So that was the initial temperature. The final temperature is coming up. Okay, so let's erase and try to analyze. Let me show you how to analyze the final temperature. Very simple. So first, so here's the plot. Let me just enlarge that plot. Let me just write down 28. Okay, so here's the plot. So first, I want to highlight the most linear portion of that plot. So which is that portion. Okay, that's the most linear. So avoid something that has kinks and some kind of features that are artificial due to somehow touching of metal suddenly with that temperature probe or something that you've done. Either you should be mixture or you've done something. But then just locate the area which is like a smooth descending temperature. Okay, but it has to be the most linear portion of that plot. So I highlight that most linear portion of that plot. I want to create a straight line. So like here's a ruler, and I want to just draw a straight line. That's all my intention. So I'm going to create a straight line. Here's a nice equation for it. Who cares? All I've done basically is, here's my straight line. I just created a straight line. Okay. So from that straight line, I want to go to analyze and just interpolate. So I'm going to bring that cursor until the initial time mixing. So this is when I mix the metal with the water. See that little kink? When the temperature starts to spike, start to jump, that's when I mix the metal with the water. Around that time, okay, can you read? So here's the window. So locate the temperature inside that window. So here's the beginning of the mixer, mixing the metal with the water. Can you read that temperature?
Is it 26.2?
Right, so 26.2. So write down that value. So the final temperature for both. So this is the temperature of the water and the metal together, which is identified as the final temperature. So that's the fifth line down. So this is 26 point. So what we said 0.2. Okay, so that's why I have. Okay, so the final temperature is 26.2. Here's the initial temperature of the water. All right, so now, so the next line, which is the change in temperature for the water. Okay, so I think the change in temperature for the water, final temperature minus the initial temperature. What's that number? So subtract 21.3 from 26.2. That's the change in temperature for the water.
Negative 4.35.
So the final temperature is 26.2. Take away 21.3.
Oh, okay.
So you're going to wind up having positive. What's that number?
$4.9.
4.9. Okay. So as far as the metal, okay, so the change in temperature for the metal, the initial temperature of that metal is the hot temperature, 90.3. The final temperature is the same as the water and the metal together, which is 26.2. So the final temperature, which is 26.2, take away 90.3. So it's gonna, turns out to be negative. So in here, you can substitute that final temperature since you know it now. So we're going to substitute that value to be $26.2. And this is 26.2. All right, and what's that difference? So what's that number for the metal? The change in temperature for the metal. So calculator, and start with 26.2. That's the final temperature. Take away minus 90.3. And what we get?
Negative 64.1.
Point one.
Yes.
All right, so this is the difference in temperatures. All right, so now eventually it gives us a little bit of space to figure out a few calculations. So let's calculate the heat due to that water side.
So the negative
Okay, correct.
64.1, that is a change of temperature in the water?
Yeah, so just subtract the two. Okay, so 26.2 take away 90.3. So that's the metal. So last value that belongs for the metal, and it's negative because the metal was hot at the beginning and cools down at the end. The final temperature is lower,
Okay.
decrease. So final temperature 26.2 minus the initial temperature of the metal, which is 90.3. Okay, so the final minus the initial is negative. All right, so how do you find the heat absorbed by the water? Okay, so this is the value of the heat. So without that negative, the heat absorbed by the water, which has been calculated for us so far, which is the mass of the water, which is ran at 74.54 grams, times the specific heat of the water, 4.18, times the difference in temperature, and he said 4.9, so that difference is 4.9. So if you multiply all these together, but show it to me. Okay, so give me the value after you multiply all these values, but then on your side, you have to show that part. So you multiply the mass of the water times specific heat of the water times the delta T for the water.
Actually, I think the change for the water is actually 4.35.
No, 4.9, all right. So so you said 4.35?
Yeah.
All right,
Professor,
And
I have
then-
a question.
yeah.
Why do we use 21.85 instead of the 21.3 from the initial time? I mean, from the initial temperature.
Right, because somehow, as I'm trying to heat up the metal, somehow there's a change in the temperature inside the water, inside the calorimeter.
Oh, okay.
It's no longer, it's no longer 21, like 21.3. It turns out to be a little bit hotter, which is 21.85. Okay, so the initial temperature of the water, I already changed it. I had it initially as based on what we seen first, 21.3, but then it heats up a little bit. So it turns out, and how to measure it, basically just follow that plateau. So if I follow that plateau, for example, so here's the initial temperature of the water, just follow that plateau. And the value is the Y value on that plateau. All right. All right, so in here, all right, so any value? So what's that value? Are you able to figure out that value? So just multiply all these numbers.
I got 1,355, negative 1,355.9.
65. Point
0.92.
92.
or
All right, so these are oranges, right?
0.93.
Okay, so that amount without the negative is the amount of heat been absorbed. So assuming the system, the same as, so here's the system. So if you look at the point of view of the water, and assuming the water is the system, anything that goes in is considered positive. Anything goes out is negative. So if the heat goes into the water, which is coming from the metal, because the metal is hot, it's going to deliver heat to who? To the water. So water took up that heat. So any incoming heat to that system of water is considered positive. In this case, water took up the heat. So think of it as your, let's say, let's say your bank account. So any incoming money, it doesn't matter if you wired money electronically or wired, it doesn't matter. So any deposit is considered positive. Any withdrawal is considered negative. Agree? So based on that point of view, if the water is the focal point, the point of view, the system that you want to study, and in this case, water took up heat, it absorbed heat. That heat is positive. So that part, so just don't think of that negative for a second. That amount of the heat, which is 1355.92, is the amount of heat the water absorbed. Okay, that's that. Now let's turn our case to the metal. Okay, so the metal is the source of that heat being absorbed by the water. It means the metal itself lost that heat. Remember my analogy, which is my $5, I give it to you. So in the whole room, there's only $5 in my bucket initially. And I've lent you, so I say I gave you $5. Your point of view is you gained $5. My point of view, I lost $5. At the end of the day, both of us, when we start the day and the end of the day, is there any difference amount of money? So let's say I gave you $5 and then you took it, then maybe you lend me back maybe a portion of it, or maybe the whole amount back to me, back to you, back to you, back to me, back and forth. No matter how do you exchange that $5. At the end of the day, when we enter the room and exit the room, at the end of the day, that $5 meant to be $5. Agree? Exactly what's going on with the heat. So the metal lost heat, and who took up that heat? The water. So the amount of exchange is the same. So therefore, there's no difference. There's no increase, decrease. The sum of all these heat exchanged is 0, because the metal delivered, let's say, plus lost 5, assuming lost that 5. Who took up that 5? The water. So the point of view of that water is positive. The point of view of the metal is negative. But the amount is 5. So plus 5 and minus 5, if you add them up, their addition is 0. So exactly that's the first proposition, the reason why we add the heat. All the heat exchange inside that container has to be 0. All right, so what's left on this side? So that measurement, which is, I'm showing that value. So you guys have to show me the whole measurement, the whole calculation for the water. Now do the same for the metal. Okay, so as far as the metal, okay, what we know about the metal, we know the mass of it, we know the delta T for the metal. What's not been known is the specific heat, but we know solid, the amount of loss, the losses, the amount of heat gotten out of the metal and delivered towards the water. So the amount of heat took up by the water is already known. On this side, what's the unknown is specific heat of the metal. So if you multiply these two and multiply this by the specific heat, so here's the specific heat of the metal. So can someone multiply these two? So 49.41 times the difference in temperatures. What's that difference in temperature? What we said, 60.1. So multiply 60.1, which is negative. Multiply this by 49.41. So it's gonna wind up having negative.
Oh yeah.
So what you got? So 60.1 times 49.41.
It's 64.1.
Oh, 64.1? All right, so this is 64.1.
Oh yeah, I also have this question for calculating the specific heat of the metal. So if the specific heat of the metal was to be calculated, would I, in this case, I'll just understand the relationship of that the specific heat of the metal is equal to the specific heat of the water, and the specific heat of the water would have to be a negative value, and the specific heat of the metal would be positive. Yeah, but I mean,
The specific heat of the material is always positive.
Yeah.
Okay, so the amount of heat to be delivered to that material, doesn't matter, metal, water, or some other substance, how much of heat you need to deliver to that 1 grammage amount of that matter, of that element, of that substance, until you increase it by 1 degree. So scoop out 1 gram of anything, so metal or water or some other substance, 1 gram. So start with 1 gram. Keep adding heat until you raise up that temperature by 1 degree.
Yep.
This is called the specific heat.
Oh yeah. So like what I was
This
just
is positive.
was the energy is opposite each other.
Yeah, so the energy exchange basically has to be opposite. So one took up the heat, the other one give up the heat. In this
And
case, the
so-
metal give up that heat, and the water took up the heat. So
Yeah,
what's
and so
the
in that,
value?
oh yeah, so in that case right here, I would just calculate the energy for the water, and then after using that, I would just negate the value for the energy for the water for the energy of the metal.
Exactly. So this is our model. So the heat exchange between the metal and the water, they're equal as far as the number, the value, but opposite in sign.
Yeah.
Alright.
And so I'm just thinking that after I just do the negation, I would just say that the specific heat of it would be the energy of the metal is equal to just all those known values just plugged into the Q equals MC delta T, and then just C
Solve for the unknown.
the unknown.
Right. So what's that number after all? So multiply 49.41 times minus 64.1. What you got? What's that multiplication?
Oh, let's see what that is. We're
You did
49.41 times the 5.
Yeah, so if you multiply minus 64.1 times 49.41, multiply this number by this number. So these are two numbers, and the middle one, the specific heat of the metal, remains to be unknown, to be solved for.
$3,167.18.
So 3,600, we said?
3,167.
67.
Point
0.18.
18.
All right, so that's the value. It is negative because that difference is negative. All right, so that will take care of that negative. Eventually, the specific heat of the metal has to be positive, okay? And then solve for it. So solve for the specific heat of the metal, okay, which is you divide by that number. And that will be it as far as your measurements for tonight. All right, so for tonight, just finalize the measurements, the specific heat of the metal. So remember, like we're approaching it by just one trial. Okay, so we don't have the second trial. So we're not gonna attempt the second trial for the same metal. So by just one trial, okay, solve for the specific heat of the metal. And then, so we don't have the average specific heat, and we don't have an unknown number, just say unknown metal. And plus, solve their post-lab questions. There are 3 questions, answer them, and just pay attention to the last question, which is a plot. So last question says, go back to that provided table that shows molar mass and specific heat of different substances. So plot their molar masses on the x-axis, plot the specific heat on the y-axis. So the y-axis represents the specific heat measurements. The x-axis represents the molar masses in this table. And then conclude. So come up with that trend line equation, conclude what's going on. As you keep increasing the masses slowly by 1, by 2, what's going on with the specific heat? Does it increase, does it decrease? So plot that table of the molar masses and specific heat of different substances based on number 3. Number 3, just simple plotting of this table divided in question 1. Okay, so what's left of this analysis? Just finalize that value of the specific heat based on one trial, and then solve for these 3 questions. And just pay attention to that plot. What does it mean?
Oh yeah, Professor, so let's see, so I did do a calculation for the energy for the water, and should I be getting 1,528 joules approximately?
But I thought, because someone gave me 13,555.92.
Okay.
So these
yeah.
are These are your numbers, I know. So you guys give me that value. So I'm not verifying. I have my calculator, but I want you guys to calculate. Okay, so not that I'm missing a calculator. I do have plenty of these, but then I'm trying to push you into making your own calculations. If that turns out to be incorrect, you're risking trusting yourself, because it's not my number. I did not calculate. So hands off as far as the calculation numbers. Verify those numbers.
Yeah,
Okay.
I did recall that the initial temperature of the water was just 21.3 degrees Celsius, and I used that number for calculating the change in temperature of the water.
Right. So there's whatever I'm showing here.
Mhm.
So it's no longer 21.3. It's whatever that newest value to be
Yeah.
recorded as the initial temperature of the water.
Mhm.
Remember? Okay. The rest of them should be fine.
Yeah, and then I can
with that
imagine that I can just negate the 1528 when I'm just doing the calculation for the specific heat of the metal. I mean, for the energy of the metal.
Right. It'll turn out to be positive nonetheless. All right. And so I similarly just solve for that specific heat of the metal.
Yeah, so let's see.
Okay.
So from what I did see is that the water temperature did rise. So in that case, so I'm just wondering, so how should it be a negative value? Let's see. So in that case, the energy for the water would be negative because of the initial relationship we had, or I'm just wondering how it should
Yes.
be a negative value.
Yes. So that negative is we impose that negative. It is artificial and imposed by us. That negative.
Mhm.
That negative. That negative is we decide to impose it. It wasn't there. So here's the water took up some heat. Here's the metal delivered or lost heat. Okay. So let's say by analogy, let's say I am the metal, let's say, and I lost $5. And you got on my $5. So I gave you $5. I lost. My point of view is I don't have it any longer. So I lost 5. Your point of view, you gained 5. You took up my $5. At the end of the day, okay, so is there any higher value than 5 at the end? So we both entered with only $5. It turns out to be in my bucket. I took it out of my bucket and I gave it to you. Okay, so I lost 5. You took up that 5. At the end of the day, do we have higher or lower value than 5? Well, there's no change. I mean, you entered, both of us entered with only $5 and we walked out from that room having still $5, either in my bucket or in your bucket, doesn't matter. But the 5 remained to be 5. So therefore, the amount of increase or decrease of that heat is 0.
Yeah.
There's no heat developed. There's no heat lost. There's no increase, decrease. I mean, the heat remains to be the heat. Whatever that quantity of heat mean you walked in. We both walked in with only $5. Let's say, assuming initially in my bucket. I took it out of my bucket and I give it to you. So you gain 5, but I lost 5. If you add them together, what's the change? What's the amount of difference? 0. Plus 5 and minus 5 is 0.
Zero change, yeah, because
Yeah, so
think
at
that's
the end of the day, inside that calorimeter, all the heat exchanges occurs between the metal and the water or some other substances. If you add them up, they'll add up to 0. Because heat goes out from one substance, end up inside another substance, onto another, and so on.
Yeah.
As if there's no losses. Yeah, as if that heat somehow transferred from place to place to place and without losing it, as if, right?
Yeah, so I'm just trying to see which Q value should be a positive and which should be negative. Yeah.
Well, depend on the process. You know, depend on the process. This time around, the metal began as hot metal and it's going to cool down. Okay, so it's going to lose heat.
Yeah.
The
Okay.
water starts as room temperature water is going to increase temperature based on what we've seen. It was around, what is that, 21? Suddenly it's going to become 26 plus. So therefore, it just gained heat. So as far as the water perspective, the point of view of water, the water absorbed heat. As far as the metal, the metal lost heat. The two quantity is the same, opposite in sign.
Yeah. So in the case of the water, it gained in temperature. So in that case, it would therefore be a positive value. And then for the Q of the water, the Q of the metal, it would be a negative value.
Yeah, so here's the water.
Yep.
Okay, we're saying the amount of heat that the water took up, okay, is the same as far as the number, as far as the value, just to grounded value. And here's the metal heat been lost, okay? So the both quantities are exactly the same quantity as far as the quantity. Whatever that number is the same as for that metal. So the metal lost it, but the water took it. That negative would say those two values, even though they're the same, but they should be opposite in sign.
Yeah.
Let's say, would plus 5 equals minus 5? No.
Yeah.
Plus 5 equals minus 5. Make sense?
Yeah, I can understand how just, positives and negatives often cancel out.
So you're trying to explain why the water is negative.
Mhm.
No, the water itself, that negative is artificial. We impose it to equate the two sides.
Yeah.
So the metal and the water heats are equivalent, except the sign. Sign is opposites. If you're not happy with that negative on the side of the water, you can shovel it to the side of the metal. It doesn't matter.
Yeah. Mhm.
But they're equal, but then opposite in sign. That's what I'm trying to say. So,
Yeah.
So
Yeah,
all I'm saying,
they're just, basically just the same distance
Five.
from 0.
if this is plus 5, how plus 5 would equal minus 5? Because one of them gives, the other one took.
Yeah.
Okay. One of them donate, the other one accept. So he's one of them. One is a donor, the other one is acceptor. Well, how that plus 5 to equal minus 5? Will never equal unless you snug in that artificial minus.
Yeah.
Now it becomes equal.
Yeah.
That's all I said. So don't worry so much about, the water gain heat. How come there's negative? There's negative when trying to equate them, when trying to lump them together.
Mhm. Yeah, so
Okay,
what it
remember-
shows is the opposite sign relationship.
Yeah, so all in all, when you add them up, they should be added to 0.
Yeah.
And that negative has to be somehow snugged into here.
Yeah. Mhm.
So if you start on one side, so a step before that step is what? Remember, I start with that step. Remember that step that I start with?
Oh, you
We
start with
exchange between them, regardless. Whatever that metal is doing, whatever that water is doing, whatever something else inside of them, assuming their third object is not just the water and the metal, some other third object, also exchange heat between the two. But all these heats are coming from all over the places, the water, the metal, and the third object, all of them, if you add them value, all of them, they should add up to 0.
Yeah.
So heat comes out from place, hop into another, then onto another, onto a third, as if whatever that amount remains to be the same, but then it hop in between places. So one place lost it, the other place gained it, and so on. At the end of the game, all these exchange should add up to 0.
Okay. Yes.
All right, and then what remains basically is answering these 3 questions. Okay, so pay attention to the last one, the plotting and the meaning of it.
Yeah, so I could probably just use the calculations for Q of water. Just, I can just, you use some algebra to just, solve for the specific heat of
Right.
water.
All right, so before leaving, okay, so in case you lost, and how would I solve for, let's say, 1 and 2, and I don't know, maybe plotting should be straightforward, I hope. Okay, so the general case of making the measurements of the Q, the heat, okay, is the following. Let me just erase. So you always start with the following. So no matter what the process is, every time you come across measuring the heat Q, every heat, regardless of being water or metal, some other substance, every Q term has in it 3 terms: mass, specific heat, and delta T. Collect these 3 parts, you'll be able to figure out the Q for that particular substance. So let's say for question 1, how much of heat required to raise the temperature of 111 grams, 111.5 grams of tin from that temperature to that temperature? Okay, so we know the delta T for that tin. The specific heat, look up the value from that table. There's a table, and it's given the specific heat. Look at that specific heat of that tin. substitute, and they give you the mass. So we know the mass, we know the specific heat from that table, and you're given the initial and final temperature. Substitute these values, here's the Q. So that will take care of number one. Number two, 100 grams of piece of metal, heat it to that degree, to that temperature, the same as what we've done in here. Dipped into calorimeter that has 300 grams of water, and the temperature initially has 7.6 value. So temperature of the metal and the water at the final temperature turns out to be lower, which is 11.2. So this time around, the initial temperature of the water is 7.6. The final temperature of both the metal and the water is 11.2. Given those facts, can you figure out the, so given that the metal so the metal is listed in the table. It's already listed in the table. Determine which metal based on that listed value. Okay, well, look, we can figure out the specific heat. So treat it the same as this experiment. So, so you need to equate the Q for the metal for question number 2. So this start with the same model as what we did for our case for this experiment. The Q for the metal is equal minus Q for the water, and substitute the given values. So you know the mass of the metal. Once again, every Q has in it 3 terms. So here's the mass of the metal. So that's the metal mass. Specific heat of the metal, we don't know. So keep it unknown. Times delta T for the metal. And that should equal minus Q for the water. Q for the water basically has in it 3 terms, which is the mass of water. Times specific heat for the water, which is known. We should know it. 4.18. Times delta T for the water. Okay, so we know the final temperature for both, 11.2. The initial temperature of the metal is the hot metal, 98.7. The initial temperature of water is 7.6. Plug in the values, solve for the specific heat of the metal, and try to see it in that table. So guess at it based on what's your number in here. So figure out which metal that is. And number 3 is just straight plotting. Okay, any other question? Are we good? So I think should be good, should not be lost. Okay, so we collected enough information to solve for the unknown tonight, for the unknown specific heat for tonight. You're left with a final calculation, get that number from that equation, and then answer the 3 questions, which is, I helped you answer these questions 1 to 3. Okay, any other questions? Any other question for tonight?
Let's see, I'm thinking I'm pretty good here. I was just trying to, manipulate the formula. I just need to base the questions off the Q equals MC delta T formula.
Mm-hmm. Yeah, so just, I mean, like for the side of the metal?
Yeah.
All right, so the mass of the metal, just substitute 100 grams. And the specific heat is, we don't know. So we're trying to calculate that value. Delta T for the metal is final minus initial. What's the final temperature for the metal?
Let's see.
Number 2. Reading number 2. So what goes for that delta T for the metal? What's the final temperature? 11.2, right? Agree? Because it says, so both the temperature of the metal and the water come to a final temperature, which is 11.2 Celsius. So that must have been the final temperature for both the metal and the water. So the final temperature for the metal is 11.2. Take away the initial temperature of the metal, which is, what's the initial temperature of that hot metal? 98.7. Agree? So substitute those values. Now to give that delta T for the metal. The mass of the water, you know it. So it's 300 grams. Specific heat for the water, 4.18. So it's 300. And what's left, figure out, multiply all these numbers by delta T for the water. What is it? What's the final temperature for the water?
11.2.
Right? Take away the initial temperature of water. What's the initial temperature of water? Based on problem 2.
7.6.
This is it. So just resolve these values. So calculate all these values. What's left unknown in that equation? The specific heat of the metal. So solve for that specific heat of the metal. Then identify this metal from that table in number 1. Okay. And number 3 should be, I believe, should be straightforward. This requires Excel plotting. What goes on the x-axis, the molar masses from that table in question 1. What goes on the y-axis, the specific heat values. So there is a good relationship between every time you increase the masses, what's going on for the specific heat. Okay, so based on that table, what's the guideline so far? So as you go higher and higher in masses, what's happening to that specific heat? Is it going up or going down? As you increase masses. So beginning with the aluminum, 26.98 molar mass of aluminum. As you continue to increase the masses, what's going on with that specific heat? Is it increasing or decreasing?
It'll increase.
They're decreasing, right?
Oh.
So aluminum has a molar mass of roughly 27 grams with the specific heat almost 0.9. Now, as you go down the list, the molar masses of the remaining of the list of the other elements increasing. So as you increase the molar masses, specific heat is going opposite. So increase the molar mass is gonna decrease the specific heat in the opposite direction. Okay, so there's a good relationship and good facts by plotting. So plot them and try to figure out what's going on. Any other question? So this is our last meeting and this is our last experiment. Any other questions or anything? If not, so I really guys enjoyed your class and helping you out with these experiments. And I hope you succeed with your last midterms and the last final.
I do have a question, actually.
Go ahead.
So I remember we were talking about the nomenclature worksheet. It still says that it's missing, even though I resubmitted it to you on a like in Canvas itself. There's an
Okay,
option.
so if you resubmit it, I'll double check. So if you
Okay.
respond to my initial comments, I'll double check. So
Okay.
if I haven't changed it and within a week from today, because today is our last meeting, give me a nudge. So send me an email, just make sure that I've changed it and I looked at it.
Okay. Thank you.
No problem. Any other concerns, any other questions? If
Thanks
none,
for all
you guys, yes, go ahead.
Oh, thank you for all the help.
Oh, thank you. No problem. So you guys have a great night, and I guess, hopefully you'll pass the 120 on to 130. And good luck to you all.
Thanks.
Good night.
Yeah, I'll see you next week, Professor.
You'll see me next week for.
Like the lab. Yeah, I was like,